Welcome back to STEM Online Academy. My name is Jason Masterakos. For those of you who know me, you know what the channel is about, right? We are an advanced mathematics and physics channel helping undergraduate students conceptually understand uh, the hardcore STEM courses. All right, so let's get right into it. Okay. Uh, what we're going to look at today is an interesting area, right? We're going to look at asymptotic integrals. Okay, it's another section of my book, Advanced Integration Techniques. If you weren't here for yesterday there was a live show on oscillatory integrals. You may want to check that out. It can help to some degree in terms of establishing a certain type of sixth sense, I like to call it, right? Quite often we need a sixth sense in mathematics. Whether it's an easy problem or a hard problem, sixth sense helps us understand things. You'll understand what I mean when you look at my other videos and you link things together in the theory, okay? All right, so let's get started. So in many advanced problems, the hardest part is not going to be just computing an integral, okay? Uh, Integrals are much harder than you actually think. Regardless, all integrals have a certain method to solving them, but uh, it's not algorithmic. When you learn basic integrals, they're algorithmic. When they get more complicated, they require, as I said, a sixth sense in terms of your problem solving skills. All right. So many advanced problems, the hardest part is not computing an integral. It's just realizing that you shouldn't try to compute it at all. Okay. No, that sounds counterintuitive to not compute something that requires you to compute. Sounds, you know, paradoxical and counterintuitive. But today we're going to talk about asymptotic integrals. Pretty much the mathematical language of approximation. It's used everywhere in uh, in physics, engineering, and applied mathematics. Right. So there's three areas where this is extremely important. Okay. So if you ever felt uncomfortable stopping before an exact answer, right, this video is for you. Okay. All right. So why exact answers? We're going to look at why exact answers don't matter. Okay, that's the first thing we're going to be looking at today. Why exact answers don't matter. Yeah, okay. So let's check that on our list. Okay, so let's look at that right now. Why exact answers don't matter. Okay. Exact answers usually don't matter. Okay, I'm going to explain why they don't. Okay. I'm sure in every calculus course you had, right? Uh, I've had as well when I was a student. We're trained to believe that the success means finding a closed form answer. But in real applications, exact answers are often unavailable, unnecessary, or misleading. Okay. So finding exact answers, don't get used to finding exact answers, especially in your careers. If you're an engineering student and you want to be an engineer, or a physics student and you're trying to become a physicist, quite often exact answers, they in school they're pleasing, but if you look for them in the natural world, quite often it will be disappointing. You won't find exact answers to solutions. Okay, so what actually matters is dominant behavior and what actually controls the size and structure of an integral when a parameter becomes large or small. Okay, so that's what really matters. Okay, what controls the size of the structure of an integral for a parameter. Okay, part two. Right. So we've already looked at that. Oh, no, we haven't. What am I saying? We've only covered part one so far. Don't worry, I don't want to get ahead of ourselves. Okay. Now, I want to talk about what asymptotic really means. Okay, what does it mean to be asymptotic? Okay, I may need a new page here. Yes, I do need a new page. Not here. Just 1 second. I need a new page to explain something. We'll look at this later. We're going to be looking at, uh, yeah, so what asymptotic really means. What? What Asymptotic, asymptotic, asymptotic. What asymptotic really means. Now, I know a lot of you, when you're thinking of asymptotic, you're thinking of a rational function, right? You know, where you have, let's say a classic example, rational function y equals 1 over x. Asymptotes are at y equals 0 and at x equals 0 uh, with the asymptotes. Nope, that's not what I mean. An asymptotic approximation, right, does not mean a rough or sloppy type function. It means you understand which part of the expression dominates a given limit. Okay, so let me put a definition here. I'm going to write it down. Okay, so I'm going to put a definition. Just 1 second. So definition. Okay, so asymptotic, right? Put right here an asymptotic approximation. And asymptotic approximation asymptotic approximation does not mean, right? Doesn't mean rough or sloppy, but an approximation that asymptotic approximation means we understand, right? We understand which part of the expression of an expression. Just 1 second here. Expression. Which part of an expression dominates in a given limit. I'm going to highlight this. So an expression which dominates in a given limit. A given limit. Okay, that's what it means to be an asymptotic approximation. All right. Given limit. Now, what we can do here is, right? Let me give you an exact definition of this mathematical definition. So if f of x, I have a function f of x, one function, and another function g of x, and we put the squiggly line here to say that they're asymptotic. Okay, we're saying that these two behave in the same way. Okay, we're saying, so here that's what it means to be asymptotic. Okay, so we're saying we are saying right, we're saying that these two behave the same way in the limit. We're saying that these two behave in a given limit. A given limit. Okay, that's what it means to be asymptotic. Okay, asymptotic means we're saying these two functions behave in a given limit the same way. Okay, so make sure that soaks in. I don't want to rush anyone watching this. Okay, that's what it means. That's what it means to be asymptotic. Okay, so we've covered what it really means to be asymptotic. Let's look at our checklist. We've talked about what exact answers don't matter, what asymptotic really means. Now we're going to look at dominant contributions and scaling. Okay. Actually, before we get to dominant contributions, we should also think about having a course shift in our thinking. Okay, that may sound a bit peculiar to people. We mean course shift. So an asymptotic way of thinking replaces one question with another, like one function with another function. Okay, like f of x with g of x, as I just mentioned, right? Maybe f of x is one statement, and g of x can be thought of another statement. Okay, what we have here. Okay, so an asymptotic approximation doesn't an asymptotic way of thinking, right? Replaces one question with another. Instead of asking what is the exact value of the integral, okay, so instead of asking what is the exact value, we should be asking which region contributes the most. Okay, and that shift changes everything. So we should be asking what region contributes the most. That's the most important. Okay. All right. So let's look at. I hope that makes sense. Now let's look at dominant contributions. So look at a dominant contribution. Okay. So what is it? Dominant? A dominant contribution. So I want you to imagine an integral over a large interval. Okay. So an integral over a large interval. Even though the domain is large, right? So even though the domain is large, uh, most of the contribution often comes from a small region. Okay. And in asymptotic analysis, this is the art of finding that region. Okay. That's what it is. Right? Asymptotic analysis is the art of finding that region. All right. And let's get into that. What do I mean by that? So we're going to look at that brings us to the next thing, right? We probably look at oscillatory, an example of oscillatory integrals and asymptotic oscillatory intervals. This would be interesting. Okay. So yes, dominance. We looked at visual idea that dominates contributions. Okay. Oh yes, possibly scaling in large parameters. Okay. We're going to be looking at an integral that has to do with a large parameter. Okay. I'm going to get to this soon. I want you guys to see it. Okay, but we're going to be looking at something that requires us to sort of get into it, right? So large parameters act pretty much almost like microscopes, right? Just like you're zooming in when you're using a microscope. They're going to amplify certain regions and suppress other regions. Now, in oscillatory integrals, the rapid oscillation is going to kill any contribution. Okay, that's how oscillatory integrals work. I talked about that yesterday in my live show. In the decaying intervals, exponential terms will dominate every area. Okay, so in decaying intervals, they will dominate absolutely every area. Okay, all right. So in decaying intervals, exponential intervals will dominate everything else in this area. All right. So I'm going to do something here. I couldn't help but calculate this interval. I'm going to give an example of an asymptotic interval, but it's also oscillatory. So if you do, I hope you understand what I mean by that. Even if you don't know the terminology, that's fine, as long as you have background in integral calculus and the will to learn, right? A strong background in integral calculus, preferably, and the will to learn, then you should be able to understand how I'm going to approach this. Okay. So we want to evaluate this integral here. Okay. So I is the integral from 0 to infinity of e to the negative x squared cosine of ax dx. Okay. Now you're probably thinking, for those of you who understand integral calculus at a deep level, how on earth can I calculate that? Okay. So we're considering an integral, right? We're considering an integral that looks a bit weird here. Okay. Um, yeah, so we're considering an integral that depends on a large parameter, let's say a, for instance. Okay. And as a, right? As a approaches infinity, not every part of the integral will survive, right? So the question is, you should be asking yourself, never can I like never, right? So the question is never ask the question, can I integrate this, right? That doesn't matter when it comes to asymptotic type of integrals, okay? Even though it does have a solution. Quick peek. Okay, so here is how I calculate it. If you want to understand how I did this calculation, okay, it's important for you to know integration by parts and Feynman trick. If you don't know what Feynman trick is, refer to one of my other videos so you can follow this, all right? But there actually is a solution to this integral, okay? If we go to page 3, continuing on, we actually get a definite type of solution here, right? It's a long integral. Okay? I mean, this is the solution that we get. But the point is, that's for you to try yourselves, to challenge yourselves, okay? The point is not to find a solution to the integral, okay? As I mentioned, right? When it comes to asymptotic integrals, it's not about whether I can compute this, right? It's about pretty much figuring out if I can actually, yeah, if I can actually figure out the concentration of the integral. Where does the integral concentrate? What's the important part of this integral? Okay, and I'm going to show you something interesting. Okay, just give me a moment if I can find it. No, did I not? No, where is it? I want to show you a simulation. Just 1 second, guys. Oh yeah, there it is. There it is. Send my garbage bin. I don't know how it got there. Okay, we're gonna look at a simulation of this type of integral, for instance. Okay, it's a asymptotic oscillatory integral. You can see here that this integral, right, has a combination of a Gaussian envelope with an oscillatory sign. What do I mean by that? The Gaussian envelope is the integral from 0 to infinity of e to the negative x squared times the oscillatory sign, as I've mentioned, right? And as you can see here, right, the sine function is very apparent, right? It's that sinusoidal periodic function, okay? So as you can see, right, the sinusoidal function, right, sine of ax, stretch to the factor of a. And we also have our envelope, e of negative x squared, e to negative x squared, which is located at that apex there. Okay, it's the blue curve, the upper part of the blue curve. Not the sine curve, the other upper part of the blue curve. That is a part of a bell curve to the right part of the branch, right? Right part of the branch is a bell curve. 1 second. Oh boy. Let me see here. Looks like something has frozen. Okay, so continuing on, right? Unfortunately, looks like my thing here is not working. All right, so what we've got, right? I was just showing you a mathematical simulation of what was happening, okay? We were just having a situation where I was showing you a mathematical model of e to the negative x squared cosine of ax, the integral of that. Okay, so let me just go back again and see if it's working. I think that was the diagnostic problem. There we go. Okay, so if you look here, e to the negative x squared and oscillator of sine x. So e negative x squared is the envelope, oscillator of sine x. You can see that we have a parameter a, right? The frequency sine ax. And you can see that the Gaussian e to the negative x squared is going to kill any contributions from zero, right? So from 0 and onwards, it kills anything far into it. Well, sine ax only oscillates inside the envelope, right? I hope that makes sense. So within sine ax, there is, I don't know why it's doing that, having a bit of a technical difficulties, no problem. But I hope that made some sense, right? That sine ax is only operating inside of the envelope, okay? Which is very important to understand, all right? Let's operate within the envelope, okay? So hopefully that gives you a geometric intuition of this integral, how this integral is behaving, okay? And as I said, I didn't go through the solution with you algebraically. Maybe you can do that yourselves. But my approach is always a step-by-step solution, right? As you can see here, again, I listed all of my steps, and I go through the mathematics step by step. Feynman trick first. I define the Feynman trick. I use the next step I use is Leibniz differentiation on both sides, differentiate on an integral sign, and then from there integration by parts, and then from there using um, initial boundary conditions, and then after substituting those initial boundary conditions into I prime of A, and then after solving for a constant K, and eventually you want to get the constant K, substitute it into the original integral, and you get a value. Okay, this value right here. All right. But the main point is hopefully you understand not just the algebra, but mainly the structure of how an asymptotic oscillatory integral is working. Okay. All right. And what does it mean to be asymptotic, an asymptotic function in the first place? Okay. All right. So we have talked about that. Talked about number 4. What about some physical insights when it comes to waves and large parameters? Okay. So when it comes to waves and large parameters, yes, there are physical applications of integrals like this. All right. So when it comes to waves and large parameters, okay, let's look at that. Actually, before saying anything about that, I do have one more other thing to say. I almost forgot. When it comes to the oscillatory decay, there are two main forces that control the asymptotics. Okay, especially of the model that I showed you. Hopefully, I can get it. I'm going to show a bit more. Okay, let me do it again. I'm going to pause in the model for a specific reason. Okay. Okay, so notice, right? I want you to notice something very important here. Okay, so notice how the sine wave is oscillating and it's compressing the Arens curve as well. So there are two main forces that control the asymptotics: the oscillation, in this case of the sine function, and the decay, and that decay is the outer blue curve, the right part of the blue curve of the bell curve, right? So the right branch of the bell curve, okay? Right. So two main forces that control the asymptotics: oscillation and decay. And the oscillation causes the cancellation. Okay. What's the cancellation is resulting from the Arens curve. The Arens curve is created from um, from the uh, from the oscillation causing the cancellation. So that sine wave produces a cancellation, the Arens curve there, which is that's representing the cancellation there, right? In the resulting curve. And decay suppresses the magnitude, right? So asymptotic reasoning tells us which one wins and where, right? Which one is more dominant. That's my point. So that's the rest of this guy here. Right, so as you can see here, I'm going to show it again. Right, so again, as I mentioned, it's very important. I want to stick it into you guys' head that oscillation and decay are the two most important when it comes to this. And the oscillation always cancels out, causes cancellation. And decay suppresses the magnitude. So asymptotic reasoning tells us which one wins and which one loses. That's what it tells us. More important than doing any of the calculations, okay? All right, so let's move on to physical insights and why this is natural, okay? So physicists use asymptotics constantly, okay? In wave mechanics, right? Okay, so in wave mechanics, large parameters correspond to high frequencies, okay? In quantum mechanics, they correspond to small wavelengths. And in a lot of these areas of science, right, exact answers are very rare, okay? So dominant behavior is absolutely everything, right? Absolutely everything. It's very important. Okay. It's very important to understand dominant behavior. All right. Okay. Now, when it comes to stationary regions, we just talk about stationary regions. Okay. This is conceptual, not technical. So one of the most important ideas in asymptotic analysis is this: only regions where the structure changes slowly survive. Again, only regions where the structure changes, right, slowly survive. So just like that model I showed you, I hope that makes sense, right? Only regions where the structure is changing, where there's a changing in the curves will survive. Everything else will cancel out. And rapid variation leads to cancellation, like that orange curve that was resulting from both the bell curve branch, the right bell curve branch, and the sine curve, right? That resulted in an orange curve that gave us a cancellation. Right? The orange curve was small because I'm trying to show that eventually it decays and then it becomes a node that's completely collinear to the x-axis. Okay, that's why there's a cancellation. All right, and let's look at maybe some common student mistakes. Okay, so what are some common student mistakes? So let me write down some common student mistakes. Students often make the same mistakes with asymptotics. It's very common, right? Number one, trying to approximate everywhere. Trying to approximate everywhere, where they should be just focusing on locally, right? So you should be focusing on local behavior, not asymptotic everywhere, okay? Number two, treating asymptotics like exact equalities. Like exact equalities. Please do not do this. That is a very wrong way of thinking. Okay. And so those are two of the common mistakes. All right. And number three is ignoring geometry. Okay. So geometry is very important. Even in the most advanced and abstract mathematics, where there's just all equations and you hardly see the geometry, don't think geometry is not working in the background. The geometry and visual spatial um, uh, mathematics is working all around us. Okay, so ignoring geometry, and scaling. Okay, that's another common mistake. All right. So how to decide what matters, right? Before touching any formulas, make sure that you're always doing the following. So how to decide what matters. How to decide what matters. And what do I mean by that? So before any formula, is there a large or a small parameter? So is there a large or small parameter? Number two, okay. Where does the integrand grow, decay, or oscillate? Does the integrand and grow, decay, or oscillate, right? And three, which regions dominate in the limit? And three, which regions dominate in the limit? Those are very important. If you can answer those, you're already understanding asymptotics. All right, so finally, why does this strengthen problem solving? Asymptotic thinking makes you faster, not because you can compute less, but because you think better. In other words, even if you don't need to know what an asymptotic function is and how it extrapolates to integration, that makes it more complicated. But even if you only understand what an asymptotic function is, it can help really increase clarity, your clarity of thinking, actually. Okay, so that alone, right, is a very, very, very powerful technique, right? Makes you faster, not because you compute less, but you think better and you stop forcing exact answers and you start recognizing geometric structure. Okay, and that can help in any course or any way of thinking for that matter. Okay. So as I said, asymptotic integrals are not approximations of last resort. They are just the natural language of large scale behavior. And once you understand that, then many advanced problems um, stop feeling impossible, especially when you see so called impossible integrals. They're not so much impossible. They just require um, techniques that you haven't learned in your elementary calculus classes, because unfortunately they don't teach calculus properly. Okay, it's not their fault. It's just the curriculum, the way it's structured. All right. All right. So that is it for today. Final thing I want to say is this structure first approach to hard integrals is developed carefully and systematically in my book, Advanced Integration Techniques, which is written specifically for undergraduates. Okay. And if you want to build this way of thinking with guidance in calculus, differential equations, or physics, I also work one on one. I'm a coach and I help one on one with coaching with students. Okay. So one on one coaching is available for calculus or differential equations or any physics course. Okay. The goal isn't perfect formulas, it's knowing what matters, how the structure works, and the applications. Okay. The links to both of those things, whether it's if you want to learn on your own, you can purchase my book in the link below in the description, the YouTube video, and or a description for coaching if you want to be able to learn to think like this in a rigorous manner when it comes to calculus. Okay, that is it for today. Have a good night, guys, and like and subscribe, please. It really helps. Bye for now.